Okay, here we go. Bismillahirrahmanirrahim. I hope you can hear me, all of you.
Class there.
Yes, sir.
Yes.
Okay,
Yes, sir.
thank you. Okay, I'll be teaching you this lecture, number 2, the remaining part of this lecture. But before we begin our remaining part of the lecture, if you have any questions in the previous 2 lectures, you can ask your questions, and then we will proceed. Okay?
Sir, slide number 22 थोड़ा explain.
Slide number 22, okay. Okay, please. Who are you? What's your name?
Muhammad Jasin.
Muhammad Yasser. Okay, please ask your question, Yasser.
सर स्लाइड नंबर 22 में जो 1/14 और 1/16 1/24 सर इसका समझ नहीं आ रहा.
Okay. Okay, you know that for a continuous beam, when it is supported on several supports, okay, the normal bending moment diagram trend is like this. Look at the arrow. Can you see this arrow?
No, sir.
Okay. The bending moment diagram you must have drawn. It look like this.
Sir, screen visible नहीं है.
Screen visible नहीं है. Okay, okay. Screen visible नहीं है. Is the screen visible now? Yes, sir.
Yes, sir.
Yes, sir.
Can you
Yes,
see
sir.
the screen now?
Yes, sir.
Okay, can you see the screen now?
Yes,
Yes,
sir.
Okay.
Yes, sir.
Okay, now look at the normal bending moment diagram that you would have several
Yes,
times
sir.
run in your analysis courses. It look like this, isn't it? Can you see the red lines that I would run just right now?
Yes, sir.
Okay, so you would have drawn a bending moment diagram for continuous beams in this manner several times in your structure analysis courses. Okay? Okay, Yasser? So there is
Yes,
a
sir.
positive
Yes,
bending
sir.
moment. There is a positive bending moment somewhere at the midspan. Okay, here at this location, and then we have negative bending moment at the supports here in this location. So the normal bending moment diagram for a continuous beam is basically a negative, positive bending moment combination in this manner. Okay, provided that the beam is subjected to uniform distributed load, just like this case. So for the design, you need to know the bending moment diagram at the midspan and at the support, and you know that bending moment at the support is negative and at midspan will be positive. Okay, so for every span between the supports, two bending moment values are to be determined from the analysis. Okay, but if you want to if you don't want to do the analysis and use this approximate method, even then you need to know the two values of bending moment at the midspan and at the support. So 1/4 is the mid-span positive bending moment value, which will be given to you from the approximate analysis directly without analysis. Like, for example, if you want to know the value of bending moment diagram for the first span, so you will have to multiply 1/14, multiply by WU, which is this uniformly distributed load, and Ln, which is this Ln, this length of the first span. So let's say the load, ultimate load WU is 2 kip per foot, and length is 20. So 1/14 into 2 into 20 square will give you bending moment, positive bending moment at the midspan, without doing the structure analysis, a lengthy procedure. Okay, and the negative bending moment will be calculated from this 1/10 and 1/11, and you can see in which situation you will select which value. So 1/14 will give you positive bending moment at the midspan. 1/16 will give you positive bending moment at the midspan, but for an interior span. 1/14 is for exterior span, and 1/16 is for interior span. Okay, and 1/14 is for interior span if the exterior support, which is this one in this case, look at this circle. If this is integral support, not a support which is like a wall, beam supported on wall. A practical situation of this will be like this. Okay, let me show you a practical situation. For example, there is a beam. Okay, there is a beam like this. Okay, at one end of the beam there is a column. Okay, the reinforcement of the column is going into the beam, and the beam reinforcement is going into the column. This can be called as integral support. Okay, then let's say there is another column here. There is another column. There is a wall here. Let's say there is a wall here, and at the extreme end also there is a wall. Okay, so at the extreme end here, the beam is just supported on the wall. There is no connection between the wall and the column. This is called as simple support. Okay, and this is called integral support because at the other end the beam and the column are integral to each other. And the integrity is provided by the reinforcement of the column going into the beam, and the beam reinforcement coming down into the column, so that this connection of the beam and column is made integral by reinforcement continuity of one member into another. So this is integral support. If the support is integral, so for this exterior, this beam, this span, this value of the positive bending moment will be 1/14. Okay, and for this span where the support is simple, the value will be, this positive bending moment will be, this support will be 1/11. The bending moment diagram will be like this. And then there will be zero bending moment here, because you know that simple support or wall, the wall and beam are not integrally connected. So there will be no negative bending moment, and there will be zero bending moment here, and the positive bending moment value will be 1/11. And here it will be 1/14. And anywhere in between, for all interior supports, for all interior spans, the value of positive bending moment will be 1/16 WU L square N. Okay, so 1/14, the difference of positive bending moment for exterior span is due to the exterior supporting system. If the exterior support is integral, then the value will be 1/14. If the exterior support is simple, the value will be 1/11. And for all interior supports, for all interior spans, the value will be 1/16. Positive bending moment value will be 1/16. I hope this is clear.
Yes, sir.
Okay. If still there is some problem, you can ask again.
Sir, thank you, sir. Sir, slide number 30 पे थोड़ा मसला है.
Negative bending moment. Do you understand negative bending moment values?
Yes,
if you
sir.
look at the negative bending moment, so negative bending moment, there are two negative bending moment values. One is for column support, the case which we were discussing right now. When beam is integral with the column, so the negative bending moment value will be 1/16. But if this beam is going into another beam, okay, like this. The previous situation was a beam into the column, but there can be another beam like this, and a beam going into this beam. Okay, so this beam is called this beam will be called a spandrel beam, the end beam, the perimeter beam. And for this case, the negative bending moment value will be 1/424, not 1/16, because the integrity between this beam and this beam is the extent of integrity between a beam to another beam is less than a beam into a column. So for this reason, the negative bending moment value will be reduced from 1/16 to 1/24. Okay, this is called a spandrel beam is the perimeter beam. So it is quite possible that sometime a beam terminates into another beam instead of terminating into a column. So if a beam terminates into another beam, then this the beam where this connection is provided will have a negative bending moment value equal to 1/24 instead of 1/16. This is the spandrel beam situation. Okay. Anything else on this slide? Next
No,
time,
sir. Thank you, sir.
we will try. Next time, I will try to develop. Samula will develop several situations, which will almost encompass all these bending moment values for different scenarios. So it will further facilitate your understanding of these negative and positive bending moments. Okay. And if you try yourself, develop several situations: a beam terminating into a beam into a column, beam on the slab, okay, and assign these bending moments to the situation which you are considering. So it will make your understanding better in this approximate procedure for analysis. Okay, and if still you have any problem, you can ask questions. Okay, next. Any other question, please?
Sir, slide number 30 पे थोड़ा प्रॉब्लम है.
This slide number 30. Yes, please. Yes, sir.
नहीं सर, वो सर आगे सर थोड़ा जो
Slide number कौन सा है?
सर 30, वो 30 पे मेरे साथ तो कोई और स्लाइड है सर. इसका जो क्रॉस सेक्शन ये है सर. सर ये वाला.
अब ठीक है? जी जी.
यस सर. सर ये जो 9.25 फीट और 8.5 फीट है सर, ये वीडियो किस तरह है?
अच्छा, ओके. अगर आप इधर देखें ना, इन दिस फिगर ऑन द एक्सट्रीम लेफ्ट, ठीक है?
यस सर.
तो ये स्पेसिंग जो है, स्पेसिंग इज फ्रॉम द इंटीरियर पार्ट ऑफ द वॉल टू द सेंटर ऑफ द बीम. फर्स्ट एक्सटीरियर स्पैन जो हमारा है ना, exterior span, the distance is counted from the interior face of that wall to the center of the beam. Okay, so if you look at this figure now, this section, this is the interior face of the wall, this is the wall, this is the interior face of the wall. So from this to the center of the beam, this distance is 10 feet, correct?
Yes sir.
So 10, and then we have assumed that our beam, which we will be designing in the next step, is 18 inch wide. So 10 minus 9 inch will give you 9.25 feet distance. Correct?
Yes, sir.
Okay. And in the next span, since this 10 feet is center of this beam to center of this beam, so 10 feet minus 9 inch and minus 9 inch, this will give you 8.5 feet. So the exterior span is 9.25 feet and the interior spans are clear distances. Okay. Excuse me.
Yes,
Just
yes,
a
sir.
moment.
Thank you, sir.
Ji, Javed. Tanvi Javed. Hello. Hey, Javed bhai.
Yeah.
How are you? What is
تمام sir.
Hello. Hello. Hello, Javed. Hello. Javed. Hello. Hello. Why? How about content? Ada mister which is a COVID-19 no meeting the postpone. Nuna pas nunga porque con cargo a un grupo kana pero padre. Our transfer can be done sure. Direct continuing education center. I see. हाँ बिल्कुल आज सब बिल्कुल रोजाना आज तकरीबन दफ्तर पर हाँ खुद यार साला की प्रोसेस है Okay. This point is clear? Yes, sir.
Yes, sir. Thank you, sir, so much.
Sir?
Anything else?
Yes, sir.
Please.
Yes, sir. In basic steps for structural design.
Who are you? Excuse
Okay,
me.
I'm Ahmed Muhammad.
Ahmad Muhammad, please ask your question and speak loudly, please.
Sir, I said in the basic step for structural design. The first step is just to find the sizes. But there is sizes for structural and non-structural elements. What does mean by non-structural element?
Please speak loudly. I can't hear you. Speak loudly, please. Ahmad, speak loudly.
Sir, I said in the basics step for structural design. For one way.
Yeah.
So the first step is to find out the size.
This one? Yes.
So yeah. Yeah, the first
Yeah.
slide number 16.
Slide number
16.
16. Okay. Yeah, this one?
Yeah, the first step.
Yes, Ahmad, please ask question.
There says like sizes for all structural and non-structural elements. What does mean by non-structural elements?
Non-structural elements,
yes.
Like walls. For example, in this case, because a wall in a frame structure, in this case, in a frame structure, when we construct a frame structure, design a frame structure, then the walls are non-structural elements because there is no load transferred through walls, and walls just act like partition walls. So all those elements which do not take in the load transfer mechanism, they are called as non-structural elements, such as walls in frame structure, partition walls, okay, like this.
Roof as well. What about roofs and floor?
If a wall is load-bearing wall, if a wall is load-bearing wall, if a wall is part of load-bearing wall system, just like in our residential buildings, in homes, where the slab is supported on walls, then the wall will be a structural element, not a non-structural element.
Okay, that meaning we mean by non-structural those elements which they are not transferring any loads.
Yeah, you're right.
Okay, that's it. Thank you, sir.
Yes, anything else? Anyone else with any other question? Okay, if there are no questions, then I think let's begin the remaining part of this lecture. I was told that you have already completed 56 slides and you designed slab using the strip analysis, because this was a one-way slab, and you were also able to design a simply supported beam. The bending moment was calculated using WUL square by 8, and then you designed the beam yourself because it was a very simple beam. But the only difference that you also learned the skin reinforcement in this example. So skin reinforcement was also very simple. You can calculate skin reinforcement by just dividing the total reinforcement by 2. And you can provide the skin reinforcement as shown in this slide. Okay, you also designed the beam for shear. You can provide the stirrups. Okay, so now the next part of this lecture. In this design example, which means the previous design example that you have already completed in the previous lecture, the beams were supported on walls. This was done to simplify analysis. You know that this was a big hall, 60 by 90 feet is a big hall, okay? And such halls are usually designed for gymnasium and for wedding halls, maybe sometimes a mosque or thing like this. And such big halls shall not be supported ideally on walls, because it's the weight of the slab and the beams. You can see that the beam is 60 feet, 60-inch deep. Excuse me, just a moment.
सर जी ये कनेक्शन में मसला है सर.
Okay. So in the first design example, the slabs were deliberately supported on walls. Why deliberately? To make the analysis simple. Because if beam is supported on columns, as you will see in the next slides, then you can't do the analysis yourself. You will have to do a frame analysis instead of simply supported analysis and using WL square by 8 equation. For practical reason, therefore, the beams must be supported on columns, and hence the structural analysis will be that of a frame rather than simply supported beam. In the subsequent slides, the analysis and design results for beam supported on columns have been provided. So now, in this case, the structural system will look like this. Can you see this slide clearly?
Yes, sir.
Yes, sir.
Okay, now what is the difference in the two cases? In the previous case, there were no columns. There were no columns. These columns were not existing. Okay. And these beams and the slab both, they were supported on walls here. There was a wall here, continuous wall. There was a wall on this side as well. Okay. So this beam which we were designing was basically supported on both ends on wall. And that's why we call this a simply supported beam, and we analyze this using WL square by 8. There will be walls in this case also, but the walls will be partition walls only. There will be partition walls between these two columns. There will be partition walls, partition walls, partition walls, partition walls. So the walls will not take part in the load transfer mechanism. Okay, this will be just non-load bearing walls transferring no load except its own load to the ground. When I say do not transfer, I mean they will not transfer any load from the structural system to the ground. Okay, the load path in this case will be like this. The slab load will be transferred to beams somehow, and then this load will be transferred to the column, and from the column, through the column, the load will be transferred to the footing foundation, and from the foundation to the ground. It will be like this. So in this case, the beam is supported on both sides. On both sides, the beam is supported on columns. Okay, so this will give rise to a frame type of structure. This is a frame type of structure. Okay, so you can't do simply supported analysis in this case. And so you must have to do the frame analysis in this case. Okay, if you take a section of this like this, if you take a section, this, so you will see a beam here, and then a slab part, then a beam, and then a slab, and then so on. Okay, so there is not big difference in the slab analysis. However, there is difference in the column and the beam analysis. If we convert this now, this 3D system into a 2D frame, so a 2D frame will look like this: a beam resting on two columns. Okay, and center to center, the distance of the beam is 61.5 feet. 61.5 feet, and WU, which is ultimate load on the beam, will remain the same because we will change nothing except changing the supports. It will be 3.355 kip per foot. Okay. Now, will there be any change in the analysis and design of the slab? I'm asking this question from you. Will there be any change in the analysis and design of slab? There will be no change in the analysis and design of slabs because the length of the slab is the same. The support conditions are almost the same. Okay. There will be change only in the analysis of the beam because the support for the beams is being changed. Okay, so in this case, the beam is supported on columns, and the analysis will be done using a frame analysis. And you know, you would have several times analyzed frames, single bay frames like this, single bay frames with a beam subjected to uniformly distributed load, and then the string on a column. Several times you would have analyzed situations like this. Okay, so you can use any method of analysis for this, but you should use exact method of analysis for this. Now you can't use the simple approximate method of analysis for this. You would have a positive bending moment and negative bending moment like this. Okay, you know how to do this using any method of analysis, stiffness or flexibility. You can analyze this system, or even using tapes, you can do the analysis. And after the analysis, you find that positive bending moment is equal to 1727 inch kip, and negative bending moment is 1407 inch kip. Okay. Okay. There is one interesting thing you should note down. That the total bending moment value between the supports, the total bending moment value. from the total bending moment value, I mean to say that the positive bending moment value plus the average of the two negative bending moment values will always be equal to WL square by 8. So if negative bending moment is 0, 0 and 0, so positive bending moment must be equal to WL square by 8. However, if there is negative bending moment at one or both supports, then the value at the midspan cannot be WL square by 8, it will be less than that. In this particular case, if you add these two values, 17,627 and 1407, it will be almost equal to, should be exactly equal to, but it will be almost equal to the positive bending moment value in the previous case, because that was the case of WL square by 8. And you can check your notes of structure analysis that it will always happen that between the supports, the total value of the bending moment will be equal to WUL square by 8. Okay, and from the total bending moment value, I mean the positive bending moment value plus the average of the negative bending moment value. This bending moment value and this bending moment value divided by 2. If they are equal, one of the two values plus positive bending moment will give you WUL square by 8 bending moment. So in this case, it is 3.355 per foot UDL is 661.5 feet center to center distance. Okay, and one other thing you should note down, that whenever you do approximate method of analysis, there is the interior distance between the interior supports, distance between the interior part of the supports, internal distance. And whenever you do the exact analysis like this one, then you should use the center to center distances. If you look at this case, we have used 61.5 feet center to center distance. In the previous case, we used 60.5 feet distance for the analysis. Okay, slab design will remain the same as I said earlier in the case of beam support walls. Main reinforcement is number 3 at the rate of 9, center to center, positive and negative both, and strike gauge reinforcement is number 3 at the rate of 9. Everything remains the same. Okay, we will just quickly go through the beam flexural design. Because we have already designed the beam for positive bending moment, so it is not difficult. We will just quickly go through this. You have positive bending moment, so you already know the steps of design for positive bending moment. First of all, you will have to determine the effective width of the beam, which you have already determined in the previous case. It will remain the same. It will not change. Everything will remain the same. Just the value of positive bending moment has changed from 19,000 to 17,000. So the reinforcement will slightly reduce. In this case, it will slightly decrease. And the negative bending moment value 1407, which is the connection of beam and column, is a new bending moment now in this case. And you can design for this negative bending moment. If you do this yourself, finally you will find that positive bending moment is 8.68 square inch reinforcement, and for negative reinforcement is 0.69 square inch. Then you can use several arrangement of reinforcement. You can try 6 number 8 in first layer and 2 number 8 plus 4 number 7 bars in second layer, just to reduce some area, because in the previous case it was 6 number 8 and 6 number 8, 12 number 8 bars. In this case, since the difference in reinforcement is very, very small, from around 9 inch to 8.6 inch square inch, so we are trying to reduce some reinforcement. So what we have done is that we are using 6 number 8 in first layer and 2 number 8 at the corners in the second layer, and plus 4 number 7 bars in the combination is second layer. So this 4 number 7 bars have been introduced instead of 4 number 8 bars. So 4 number 8 bars have been replaced by this 4 number 7 bar. This is the only difference in the positive reinforcement. Okay, finally the reinforcement of this, if you recalculate this reinforcement, comes out to be 8.8 square inch, 8 into 0.8 plus 4 into 0.6. So the actual reinforcement will be this. Negative reinforcement is 2 number 6 bars, because it is 0.69 square inch. So only 2 number 6 bar will be enough for negative reinforcement. And the shear reinforcement of the beam will remain the same as in the previous case. Okay. Next is the design of column. From the analysis, we have calculated that at the beam column connection, there is a bending moment, negative bending moment, which will be transferred to column 1407 inch kip, and the ultimate load, which is coming from the beam, is 103.17 kip. So the axial load diagram will be like this, and the bend moment diagram will be like this. Now we can also design this column. The column size we've assumed 18 inch by 18 inch, and I hope you remember this method of column design using the ACI design aid. It is very simple. You know PU and MU. It's coming from the analysis. Calculate the ratio gamma for 2.5 inch cover. Gamma is equal to H minus 2C divided by H. C is 2.5 inch, so 18 minus 5 divided by 18 is 0.72. So you should select now the relevant chart, design chart. Kn value is Pu divided by phi FC prime AG, and Rn is equal to Mu divided by phi FC prime. Everything is known. Pu phi is 0.65 for tied column. FC is 3 KSI. AG is the gross area of the column, which is 18 by 18 in this case. Column size 18 by 18. And Rn is equal to Mu. Mu is bending moment 1407 divided by phi FC AGH. So once you determine these two values, you select the relevant value, the relevant design chart, interaction diagram from the interaction diagram. Okay, from the interaction diagram, these two lines meet here, which corresponds to a design chart, interaction diagram from the interaction diagram. Okay, from the interaction diagram, these two lines meet here, which corresponds to around 1%, slightly more than 1%, or exactly 1% of the reinforcement. So 1% of the reinforcement is the minimum requirement of the ACI code. This 1% of reinforcement means that 1% of the gross area of the column. And the gross area of the column in this case is 324 square inch. 1% means 0.01. So the reinforcement required is 3.24 square inch. 3.24 divided by 0.44 will give you a reinforcement 7 bars or 7 point something bars. As you know that we cannot provide 7 bars in a square column. We must have to provide the number of bars, which should be multiple of 4. So we round this to 8 bars. This will be 8 number 6 bar. It will be like this. 3.24, if you want to calculate the area, divided by 0.44. So the number, this is the number of bars, n. Number of bar n. Calculate these bars. Comes out to be how much? .36 bars. 7.36 bars are required. We will round this to 8 bars. 7.36. We will round this to 8 bars. Okay. Next is ties. According to the ACI code, the ties shall be provided according to this criteria. 16 into diameter of the main bar. Diameter of the main bar are number 6 bars. So 6 by 8 into 16, this comes out to be 12 inch center, or 48 into the diameter of the tie bar. Tie bar is 3 by 8, so 3 by 8 into 48 is 18 inch center. Least column dimension means, for example, if column is 12 by 18, so least column dimension is 12 inch. Since this column is 18 by 18, so the least column dimension is also 18 inch. Finally, we decide to use number 3 bar at the rate of 9 inch center instead of 12 inch center. So further reducing spacing between the ties. Okay. This will be drafting of the column. 8 number 6 bars. You can see 8 number 6 bars. Then you can also see number 3 strip at the rate of 9 center to center. This is elevation, cross-sectional elevation, and this is the plane cross-section of the column. Okay, next is the design of footing. Okay, the isolated column footing, square or rectangular, are designed in this manner. The reinforcement will finally look like this. You have already learned how to design a isolated column footing in your previous course. Okay, you will follow the same steps. First of all, the given data to us is there is a column 18 by 18 inch. We have a concrete strength of 3 KSI to be used in footing. FY grade 4 steel will be used, and the liable bearing capacity 2.204 K per square foot, which will be ideally given to us from a geotechnical report. Okay, a reaction at the support should be used in the design of footing. Factor load on column reaction at supports. After you finish your analysis, you will, when you do the frame analysis like this, so you will finally determine these reactions, and these reactions will be applied as load on footing. Okay, these reactions, this will come from the analysis. And for the size of footing, you would require ultimate load as well as service load. Okay, so the analysis is usually done with service loads, and finally they are factored to calculate factored loads and factor bending moments. Okay, so it's very easy, you can do this. Service load on the column is 81.87 kip without factors, and factor load is 103.17 kips. Okay, in the beginning, we should assume some thickness of this concrete pad, isolated column pad, isolated column footing pad. This H is 15 inch. Okay, if you remember in the previous course, we have said that the thickness of the footing shall not be less than 12 inch because of the requirement of cover, 3 inch cover. So if 3 inch cover is required, then the effective depth will be substantially reduced. For this reason, normally the footing thickness for isolated column footing are taken as 12 inch. Okay, in this case, we have chosen 15 inch thick plate, though you can also choose 12 inch thick footing plate. The average D, why are we writing D average? Because the reinforcement will be provided in both directions, in this direction as well as the other direction. So, and because it is a square footing, so for a square footing, we'll design only one reinforcement along one direction. Okay, reinforcement along one direction. And since effective depth will be different, because one layer will be placed in this direction, other layer will be placed on top of this, the effective depth will be different for two directions. So for this reason, we are using the average, and when we use the average and calculate the reinforcement, that reinforcement will be provided with the same spacing in both directions. Total thickness of the footing is H, clear cover is 3 inch, and let's say we assume in the beginning that number 8 bar will be used. So number 8 bar, if it is used like this, this will be 3 inch cover, and the average means the contact point of these two, contact point. So the contact point of these two means that one complete bar a diameter will be added with this 3 plus 1 inch. Okay, and this total D is 1 inch, which is the diameter of one bar. Okay, this will be deducted from this for D average. This will come out to be 11 inch. Then assume depth of the base of the footing from ground level. This assumption will be practically based on the availability of the firm strata, solid strata below the ground level. This is not necessary that it will always, it is not necessary that it will always be 5 feet. It can be 5 feet, 4 feet, 6 feet, depending on the availability of the firm strata. So in this particular case, we are assuming that the firm strata of soil is available at 5 feet. Okay. Then the weight of fill in concrete footing shall be deducted from the bearing capacity in order to calculate the net bearing capacity. So this weight is gamma fill. It will be like this. This part, this H part, this part. This is gamma fill Z minus H. This is total is Z and this is H. So this part is Z minus H. This part is Z minus H. This part is Z minus H. This will be multiplied by gamma fill. Gamma fill means whatever fill material you want to use to backfill this part, because this total area would have been excavated. This total area would have been excavated in order to make this foundation. So once this foundation is completed with concrete, then this remaining part will be backfilled. This must be backfilled. Okay, this must be backfilled. So gamma fill is basically the density of the backfill material. Backfill material. This gamma fill is the density of the backfill material, and Z minus H is the depth through which this backfill will be provided. And gamma C is the concrete density, and H is the thickness of the footing. So this weight is equal to 100 into 5 minus 1.25 plus 150 into 1.25. This comes out to be 562.5, and this is 0.5625 kip per square foot additional load on the soil here at this level. Now, effective bearing capacity will be calculated from this allowable bearing capacity minus this additional load which is coming from backfill and the foundation weight. 0.5625 is 1.642 kip per square foot. And the bearing area is service load divided by QE. Service load is given 81.87, unfactored load divided by this effective bearing capacity. So the required area is 49.86 square feet, and the square root of this will become around almost 7 by 7 feet foundation. Next is to determine critical parameter in order to confirm the thickness that we will assume, because the thickness of the footing pad will be governed by the punching shear criteria. The punching shear criteria will basically determine thickness of the footing. So for punching shear, you know that this critical parameter is calculated. In critical parameter is this yellow line, the yellow parameter. Okay, we know that if column size is C and this part is D by 2 and D by 2, so this length of the yellow one side will be equal to C plus D average. There will be C plus D, C plus D, C plus D. It will be 4 into C plus D. We know that column size is 18 inch and average depth of the effective depth of the footing is 11 inch. So 4 into 18 plus 11 is 116 inch. Okay, bearing pressure for strength design of footing. For the size of footing, the plane dimension of the footing or size of the footing, we use service load divided by the effective bearing capacity. Why do we do this? Because in the calculation of bearing capacity, factor of safety has already been considered. In the calculation of bearing capacity, a factor of safety has already been considered. So when we calculate the size of the footing, we use service load divided by the effective bearing capacity. Because if we use factor load in the calculation of size of footing, then it will give us unnecessarily larger size of footing with double factor of safety. So one factor of safety has already been considered in the calculation of bearing capacity, because the bearing capacity calculation, I think now you know that bearing capacity is calculated in the lab doing direct shear test or SPT test or other relevant tests. Okay, and then the ultimate bearing capacity divided by factor of safety, and that gives us allowable bearing capacity. So in the calculation of size of footing, allowable bearing capacity, and then allowable bearing capacity is converted into so factor of safety has already been considered in the calculation of bearing capacity and double use of factor of safety. However, in the case of calculating bending moments in the floor divided by the area will give us a 2.105 kip per square upward pressure, and this upward pressure will give us now this upward pressure applied from beneath the footing by the side, because when this column takes all the load from the beam, it will transfer this load to the foundation, and the foundation, this pad will transfer this load to the side, and the side in turn, if the side does not settle, it will resist this load, and when it tends to resist this load, this pad will be lifted up from the sides, because it cannot be lifted, the load is coming through the column, so it cannot lift the whole column, but it can lift the far ends of the pad. So the far ends of the pad will be lifted up, giving rise to a negative bending moment here at this edge of the column. Okay, and similarly, when column tends to transfer this load through this footing pad to the ground, then there is a possibility of making a hole in this footing pad, just like a needle resting. If you want to push a needle through a piece of paper, so it is likely that a piece of paper will be punched or a hole will be made in the piece of paper until unless you increase the thickness of the piece of paper. So if you have a considerable thickness of the piece of paper, then it will be difficult for the needle, when you push the needle through the piece of paper, to make a hole in it. In the similar manner, we increase the footing depth in order to avoid this punching of the column into the pad, or making a hole in this pad. Okay, so this is avoided in this manner. Okay, the punching shear value can be calculated from this equation: QUB square minus QUC. What is this QUC plus D average? Instead of calculating this punching shear value at the face of the column, we calculate this value at a distance of D by 2 from the face of the column, because the hole will be made here at the boundary of this red area, not at the face of the column. For practical reason, if you construct a column, okay, and extend its reinforcement into the foundation and apply a load on the column, so the column will make a hole. The load will basically make a hole in the pad, but this hole will be made at this yellow boundaries, not at the perimeter of the column. So for this reason, this area, red area, must be deducted. This area, red area, must be deducted from the total load. So the total load, the total bearing, the total pressure which is applied from the soil in the upward direction will be equal to QUB square minus QUC plus D average, because this part is done. This part will be going into the foundation along with the column. This part will be going along with the column. Okay, if I show you an animation, it will look like this. An animation will be like this. So the hole will be, so the perimeter, this is the perimeter, okay, at which this hole is made. So this area, which is the remaining area, will be considered in the calculation of this punching shear. We discussed this in the previous lecture. If you have any difficulty in understanding this, you can study the previous lectures. Okay, and still, if it is not clear, you can ask your questions in the next lecture. Anyway, when this punching shear is calculated in this manner, 90.85 kip is the punching shear calculated now. The bending moment is calculated by this equation, mu is equal to QU k square divided by 2. How is this done? You know that this is a square footing, so the bearing pressure per square foot is QU. Okay, and if you want to calculate bending moment at this location, we will multiply this QU with this B in order to calculate the bending moment per foot, load per foot in this manner. QUB, this is the load now in the upward direction. And the bending moment will be calculated at the face of the column. So this QUB is the load acting in the upward direction, and MU here can be calculated very simple, QUB times K into K divided by 2, just like a cantilever beam. So this bending moment is QUB K square by 2, and K is basically the distance from the face of the column to the far end of the footing, which is B minus C. B is the total width of the footing, and C is the size of the column. So K will be equal to B minus C divided by 2. Because this total distance is B, and this is C. So B minus C will be the remaining distance, and this will be B minus C by 2, and this will be B minus C by 2. Okay, and the bending moment is calculated at this location. We QUB into K square divided by 2 at this location. Because this, when the column tries to push this pad down, the pad will move up like this. Giving rise to a negative bending moment at this location. Okay. So once bending moment is calculated, you can design this. Right? Design for punching shear. The punching shear design is very simple. You just compare the punching shear demand with the punching shear capacity, which is 5.4 FC prime B naught D average. 5.754. FC prime is 3000. B naught is calculated in the previous slides. D average is 11. Divide by 1000 will give you the value in kip. So 5.4 FC prime B naught D average is 209.66 kip, which is greater than the VUP, the shear demand. So the assumed thickness is enough, or even it is slightly more than what should have been assumed. So if you want to, you can reduce this a little bit from 15 inch to 12 inch. Okay. So there is a slight margin of reduction in the thickness of the footing. Anyway, we are not doing this in this example. We keep our thickness equal to 15 inch. Design for flexure. MU is equal to 668.6 kip inch. So assume small a equal to 0.2 into D average, 2.2 inch. AS is equal to this. Similar to what we have done in several lectures. Small a, again, you can use small a, and from several trials, finally, you calculate AS is equal to 1.71 square inch. But the minimum area of steel that we will be using in our examples for isolated column footing is 0.005 BD average, which gives us a value of 4.62 square inch. So the AS minimum governs, and AS minimum is 4.62 square inch. If you remember in the previous classes, I told several times in the class that although HCI code allows you to use this AS minimum value equal to 0.0018, which is the value minimum reinforcement value that we use for slabs. But from my practical experience and from the experience of several other designers, in the case of isolated column footing, it is better to use the minimum reinforcement which is the minimum reinforcement used for beams, which is 0.005 BT average instead of minimum reinforcement of the slab. Okay, because isolated column footing, there is no redundancy in isolated column footing. This is just one column is supported on this footing, and if any problem happens to this footing, then the whole structure can be in danger. So for this reason, this is my recommendation that minimum reinforcement in the case of isolated column footing shall be 0.005 times BD average and not 0.0018 BD average, which is given in the ACI code. Okay, because if anything happens to footing, it becomes very, very difficult to rectify the problem. Okay, the remedy is very difficult. You will have to excavate the footing, and in order to correct the problem, rectify the problem, a lot of effort will be required. So it is better to provide more reinforcement in the case of isolated column footing, okay, which is 0.005 BT average, 4.62. The spacing can be calculated as follows. The total area of shell is 4.62. Let's say number 8 bars are used, so 0.86 bars are required. And if you want to do spacing, so there will be a 3-inch cover on this side, 3-inch cover on this side. So the total is 7 feet, 7 feet minus 3 inch minus 3 inch. The remaining space is 6.5 inch. So spacing 6.5 feet, 6.5 divided by 12 divided by 5. 5 are spacing. 1, 2, 3, 4, 5 spacing. So spacing, the distance is 15 center to center. Okay, and 6 bars can be provided in the foundation if they are placed at 15 center to center. Maximum spacing should not exceed 3 inch or 18 inch. Drafting should look like this. Okay, now look at some of the practical pictures now. These are our own designs that we have done. Okay, in the picture on the right, you can see beams. The beams have been, the cage of the beam have been prepared, but they have not been lowered or been placed in the farm work. The beam cage has not been, the beam cages have not been placed in the farm work. Okay, this one has been placed, this one has not been placed, and now once they are placed inside the farm of the beam, okay, the slab reinforcement, you can see the slab reinforcement. Now the slab reinforcement is passing through the beam reinforcement like this. The beam slab reinforcement is passing through. This is the slab positive reinforcement, not the negative reinforcement. So you can see that some part of the beam is integral with the slab. This part of the beam, which is around 5 or 6 inch, depending on the thickness of the slab, is within the slab. So this part is this part of the beam is casted with the slab. Okay. These are negative reinforcement. Negative reinforcement particularly at some ends. Skin reinforcement can also be seen here. Skin reinforcement to the depth of the beam. And this is the finished product. You can see the formwork is being removed. You also can see stirrups here. This is a column picture. Okay, now I will show you one of the main halls that we recently designed. This is Government Girls High School, Haripur. Can you see these sheet? Hello? Can you see the sheets?
No, sir.
Okay. Total house here. Whole screen. Interesting. Okay, I hope you can see the screen now.
Yes, sir.
Okay, this was one of our recent projects. This is Government Girls High School, and the size of the hall is almost the same as we have done in this class. Hall size is 40 by 70 feet instead of 60 by 90 feet in our example. Okay. This is the excavation plan, foundation plan. In this case, we have provided a continuous foundation, instead of isolated foundation. Because the columns are closely placed in the bearing capacity such that the two isolated column footing were meeting with each other. So instead of providing them separately, we provided a continuous footing like this. Reinforcement is provided in this manner. This is the column reinforcement. Here we have provided 12 number 6 bars. The plain beam has been provided. These are the beams now. The beams have been provided in this manner. You can see now the beam with skin reinforcement. You can see the skin reinforcement. You can also see the positive reinforcement here. Instead of 12 number 6 bars, in this case we have provided 1, 2, 3, 4, 5, and 2. 7 number 8 bars. Okay, because in our case, in our example case, the beam was 60 feet long. Here the beam is 40 feet long. So 7 number 8 bars have been provided with skin reinforcement. Please. Slab reinforcement is almost the same as we have provided in our case, with the only difference that we have provided half-inch bar instead of 3 by 8 inch bar, and it has a practical reason, because sometimes the availability of 3 by 8 inch bar becomes a problem. So for this reason, we have recommended half-inch round bar and not a 3 by 8 inch bar. Although we could also recommend 3 by 8 inch bar. Okay. Okay. Do you have any question now? Yes. Because in the next few slides, we are going to discuss some case studies. You would have seen in the two different scenarios that one was the case when the slab in all the beams were supported on walls on all sides. And then there was another case when there was a system where the beams were supported on columns. Okay, but in both the cases, the distance between the beams was 10 feet. Center to center distance between the beam was 10 feet. You can ask a question why the distance between the beams is kept as 10 feet. Why not 10 feet? Why not 9 feet, 12 feet, 15 feet or so? Okay, because in the beginning, when you start assuming a structural system configuration and provide beams at certain spacing, you need some guidance for that. Okay, and this guidance comes from experience. I will share with you next slides where you will be able to see what happens when we increase or decrease spacing between the beams. Okay, because this whole design will depend on the distance between the beam, spacing between the beam. Okay. So in the subsequent slides, two case studies are carried out to investigate the variation of movements in beams, movements and slab thickness due to change in spacing between the beams. Case study number 1: variation of slab thickness and movement in between the beams. Okay, now look at this carefully now. We are changing spacing between the beams from 10 feet to 20 feet. This was the case that we have completed right now. If we increase the spacing between the beams from 10 to 12 feet, then the slab thickness will change from 4 to 4.8 inch. Bending moment in the slab will change from 19.97 to 29.5, and obviously it will increase because we are increasing the distance. By increasing the distance between the beams, we are in fact increasing the slab span. Okay, the span of the slab we are increasing, because the distance between the beams is giving the span of the slab, giving to us the span of the slab. A slab is resting between the beams. The slab part is between the two beams. So when we change the spacing between the beams from 10 to 12 feet, obviously the span length of the slab will increase, and thickness of the slab depends on the slab span. So the thickness will increase, the bending moment will increase, and the area of seal will also increase, and the spacing will decrease. Spacing between the reinforcement will decrease. If we further increase the spacing between the beams and make it 14 feet, then the slab thickness will further increase. But it will not change our design, because in our design we have already used 6-inch slab. So the same 6-inch slab will be used. Okay, the bending moment will increase, and the area of seal will also increase, and the spacing will now change from 9 to 5 inch. So the spacing is decreasing from 14 to 16 inch. Now the thickness of the slab also need to be increased from 6 to 7 inch, though the requirement is 6.4 inch. The bending moment increases from 19.97 now to 58.1. Area of seal required is 0.28, and the spacing is now 4 inch instead of 9 inch. Further increase will further increase the thickness of the slab, bending moment of the slab, area of seal required, and the slab, the seal reinforcement is almost the same. Further increase from 10 to 20 feet will make the slab equal to 8 inch now. So you will require 8-inch slab thickness, and the bending moment, reinforcement, and the spacing you can see. Which means that by increasing the spacing between the beam will effectively increase the span of the slab, increasing the thickness of the slab, increasing the reinforcement, requirement in the slab. Okay. So the trend is like this. When you keep on increasing the spacing between the beams, the thickness of the slab will keep on increasing. So for a 20 feet span length or 20 feet spacing between the beams, the thickness, 8-inch thickness is required. This is the change in maximum bending moment with the span or spacing between the beams like this, because it is L square, so it is not linear, it is bilinear. Now it will also, when you change distance between the beams, then load on the beam will also increase. Okay, load on the beam will also increase, because center to center distance between the beam will, the change in center to center distance between the beam will change the load on the beam, every beam. So if instead of 10 feet center to center beam, we reduce this spacing between the beam from 10 to 5 feet, then the positive bending moment is this much, negative bending moment is this, and the area of shield is much smaller than the area of shield that we have used for 10 feet spacing. 8 feet spacing will give us these values. 10 feet we know already. 12 feet will increase the bending moment, will increase the negative bending moment, will increase the reinforcement. And 14 will it increase substantially, 10.93. And imagine if you make this 20 feet. So 20 feet will give us around 15 square inch of reinforcement. And you have seen in the previous case of 10 feet that placing 12 number 8 bars is also not easy. In a 60 feet long beam, 12 number 8 bars. So this these case studies will enable you to understand the difficulty in increasing spacing between the beams. If the spacing between the beam is increased, then the demand on the slab will increase, the demand on the beam will also increase. So we must have to select a compromising situation. You to decide a compromising situation. Okay, if we keep the spacing too small, then there will be too many beams and too much of reinforcement. If we, on the other hand, the spacing between the beam is too large, then it will be the number of beams will be less, but then every beam will have a lot of reinforcement. So we have to find a middle way in these two extremes. And the middle way in these two extremes again can be not a single solution. If in the case that we were discussing, we had selected 10 feet center to center. You can select 8 feet, 9 feet, 7 feet. These are reasonable. Okay, but too close spacing will give you too many beams, and then the placement of the beam, the form work, everything will become difficult. Okay, so in this manner, we select the spacing of the beam. This is the spacing between the beams, bending moment change in the spacing of the beams. What are the conclusions? The conclusion of the slab thickness increases by increasing the spacing between the beams. The reason is very obvious, because the span length of the slab depends on the distance between the beams. And moments in slab increase by increasing the spacing between the beams. This is also very obvious, because by increasing the spacing between the beams, the load on the beam will increase, because it will have to support now more part of the slab. And moments in beams also increase by increasing spacing between the beams. Okay. Summary of this lecture is ACI approximate method, bar spacing is this, shrinkage and temperature reinforcement, maximum spacing, and all this. This is the end of this lecture. Okay, if you have any question, you can ask your questions. Otherwise, the lecture ends here.
Sir? No,
Please. Who are
Sir,
you?
I am Ahmed.
Ahmad. Yes, please, Ahmad, ask question. But speak loudly, okay? Loudly and slowly.
Okay, no problem. Sir, in the beginning, there you have explained for us the integral support between column and beam,
Okay.
and also between the simple support between column and beam too. But within the lecture, we have shown us that in the real fields there is integral between slab and beams. Can you explain that situation and why that?
Yeah. This is very simple. A slab finally terminating into a beam, which is very usual situation. I can explain this.
Yes, please, sir.
Okay. Ahmad, can you see this picture?
Yes, sir, I can see.
Okay, you can see this slab reinforcement is going into this beam, okay?
Yes.
What will happen at the terminal end of the slab? The terminal end where the slab ends, this reinforcement will terminate into this beam.
Okay. Doesn't that affecting the load mechanism of slab, which is transferred to the beam?
Please say again. Please say again.
I said does it that affect the load which is transferred from the beam, from the slab to the beam?
I'm sorry, I couldn't understand your question.
Okay, like if there is no any integral between the beam and the slab, so the support between the slab and the beam is obviously simple, right?
Yeah, it's simple. Yes, like a
But
slab
not-
resting on a wall. Slab resting on a wall.
Yeah, it is in like for the frame, the slab is resting on the beam and the wall too.
No, but the wall, if the slab reinforcement is terminating in a beam, and below the beam there is a wall, then in that case the wall is not integral with the beam and neither with the slab. Okay, and the wall will be more likely a non-partition, non-load bearing wall, a partition wall in that case.
Okay, there is no such situation that three of them, like slab and beam and wall, they are integral.
It is possible, but if wall is concrete.
Okay, that's clear.
If wall is concrete, then the wall the wall reinforcement will be extended into the beam reinforcement. Okay, so the wall will be integral with the beam, and the slab will be integral with the beam. So the slab is integral with the beam, and the beam is integral with the wall, and the wall is concrete. But if wall is brick masonry, then brick masonry has no reinforcement. So the connection between the brick masonry wall and the concrete beam is not possible.
Okay. In this situation, in the picture, the left one, does this situation affecting the calculation of the moment?
Calculation of the moment. I'm sorry, I couldn't understand the question.
Like you've told us how to calculate the moment when there is integral between column and the beam.
Yeah.
So it's different than the simple support between beam and the column too. So in this situation, does it affect it or not?
You mean the slab action will be affected or not? The slab action, you mean?
Yes.
At the terminal end, you mean?
In the terminal or within the center of that slab, like the slab
Within
on
the center of the slab, if there are two integral supports, like look at this case, this beam and these beams. Okay, the slab reinforcement is going into the beam, and the beam reinforcement in the form of strips, and the form of strips is going into the slab. So these are integral. The beam is acting as an support for the slab. Correct? Correct? Okay, Ahmad?
Yes, your voice has disconnected. Then just repeat it again,
Okay.
please.
Hello, Ahmad? Hello? How is
Yeah, I can hear you now. Yes.
Okay. Though, although I couldn't understand your question, but I will try to explain that when the slab reinforcement is going into the beam reinforcement, and the beam reinforcement in the form of stirrups, because the stirrups are common now in this part. In this part, the stirrups reinforcement are basically will be cast within the slab concrete. Okay, so the slab reinforcement in the form of stirrups is extended into the slab, and the slab positive reinforcement as well as negative reinforcement will be casted with this remaining part of the beam. So slab and beam in this case will be integral to each other. Okay.
Okay.
However,
I thought just one strip. That's why I have asked the question.
Okay. So your question is answered or not?
Yeah, I have understood now. Thank you so much.
Okay, Ahmad, good question. Any other question? Anyone else with another questions?
Shumi sir.
Yeah, please. Who are you?
सर ये यासर खान सर.
Yasir Khan, please.
सर ये आपने केस स्टडी में जो डिस्कस किया ना सर, आपने कहा कि अगर हम स्पेन लेंथ को 10 से 12 करेंगे, 12 से 14 करेंगे तो मूवमेंट पर ये इफेक्ट आएगा और हमारे साथ स्लैब थिकनेस पे ये इफेक्ट आएगा ना सर.
हाँ हाँ.
तो सर अगर हम जो है ये इसको मतलब 10 से कम करेंगे तो क्या इफेक्ट आएगा सर?
अगर 10 से हम कम करेंगे तो you have seen that what happens with what happens to the slab. What happens to the slab with 10 feet? With 10 feet, the slab thickness comes out to be around 3 point something. Okay, and we assume 6-inch slab.
Yes sir. सर लेकिन ये जी सर.
Okay, further reduction in the distance between the beams will have very least effect on the thickness of the slab, because the thickness of the slab, there must be a minimum thickness of the slab, and that minimum thickness of the slab practically in these days, in current days, is around 5 to 6 inch for good concreting and all this. So you cannot reduce the thickness of the slab beyond 5 inch. Okay, so
Okay.
the effect on the slab thickness, if you reduce spacing between the beams, so it will have either no or very marginal effect on the thickness of the slab, because there must be some minimum thickness of the slab. So further reduction in the spacing will not change the thickness of the slab. And similarly, there must be some minimum reinforcement. So there will be no change in the minimum reinforcement in the slab, nor in the thickness of the slab. However, there will be change in the reinforcement of the beam, because by keeping the beam closer, load on the beam will reduce, and when load on the beam is reduced, the bending moment will reduce and the reinforcement in the beam will reduce. Okay.
Yes sir.
Okay, I can show you the comparison once again. If you look at this slide, can you see the slide?
Yes sir.
Okay, with 10 feet spacing, the slab thickness is 4 inch, but you have used 6 inch. So further reduction in this will not change this 6 inch slab.
sir.
Okay. Hello. Okay.
Yes
Okay,
sir.
sir.
And similarly, the reinforcement is already minimum. So further reduction in the spacing between the beam will not change the reinforcement. So it will have a least advantage to us in terms of slab thickness and reinforcement in the slab. However, it will have an advantage in the beam reinforcement. If you look at the next slide, this one. So from 10 feet, when we reduce the spacing to 5 feet, there is a substantial decrease in the slab and the beam bending moments and the beam reinforcement. Okay, though there will be no change in the slab thickness and the slab reinforcement. Okay, yes, sir.
Yes sir. Thank you sir.
Sir?
Anything else? Ji, please.
Yes, sir.
Ji.
Sir, अगर हम जो है,
Any other question?
yes, sir, I have a question, sir.
Ji, please. Who are you?
Zakaria Khan, sir.
Zakaria Khan, please ask your question.
Sir, अगर हम one-way slab construct कर रहे, but it is resting on the columns and then there are beams and columns. सही है sir, frame structure है. तो उसमें सर तो सर अगर हम डिस्टेंस बिटवीन टू कॉलम्स हम इंक्रीज कर रहे हैं तो उसका सारा इफेक्ट तो सर बी कॉलम पे जाएगा ना सर। उस पे तो स्लैब पे तो कोई फर्क नहीं आएगा उसके थिकनेस पे।
यानी आप कहते हैं कि बीम की स्पेसिंग हम इंक्रीज करें या कॉलम की स्पेसिंग?
कॉलम की सर हम कॉलम की स्पेसिंग इंक्रीज कर रहे हैं और ये फ्रेम स्ट्रक्चर है हमारे पास सर, तो उस
और
पे
नहीं
तो
तो
बीम
फ्रेम स्ट्रक्चर तो बीम की स्पेसिंग भी बढ़ जाएगी ना।
तो सर बीम की थिकनेस हम इंक्रीज करेंगे ना, फिर स्लैब पे तो कोई इफेक्ट नहीं
बीम
होगा।
की स्पेसिंग भी बढ़ जाएगी ना।
स्लैब पे सर स्लैब थिकनेस विल रिमेन द सेम।
डिपेंड करता है कितने आप बढ़ाते हैं ना। इस तरह हमने इसमें किया हुआ है 10 से 12 फुट के, तो इतना असर नहीं पड़ा, लेकिन जब उससे भी ज्यादा हम करेंगे तो फिर फर्क पड़ता है।
ओके सर।
एक्सक्यूज मी
Anyone
सर।
else?
यस
जी
सर।
जी।
सर मेरा
Who are
क्वेश्चन
you?
टॉपिक मोहम्मद साद सर।
मोहम्मद साहब प्लीज।
सर मेरा क्वेश्चन इस टॉपिक से रिलेटेड तो नहीं है, लेकिन एक प्रैक्टिकल एग्जांपल चाहिए थी
अच्छा पूछिए
सर।
फिर आप।
सिंपली सपोर्टेड फ्रेम की प्रैक्टिकल एग्जांपल कोई दे दें।
स्लैब या बीम दीवारों के ऊपर पड़ा हो, ये सिंपल है। ये क्या है?
सिंपली फ्रेम की सर, फ्रेम की।
फ्रेम तो सिंपल नहीं हो सकता ना।
मतलब सर एक साइड पे रोलर है और दूसरी साइड पे हिंज, या दोनों साइड पे हिंज।
हाँ, तो दिस नॉट ए फ्रेम। ये फ्रेम नहीं, ये बीम आप बता रहे हैं, दिस इज ए बीम। ठीक है।
यस सर।
आपका क्या नाम है साहब? दिस इज ए बीम,
जी।
ओके, दिस इज नॉट ए फ्रेम। इसकी मिसाल ऐसे है कि एक साइड पे दीवार है। आपका क्वेश्चन ये है कि एक साइड पे रोलर, दूसरी साइड पे हिंज है।
एक फ्रेम सर, एक फ्रेम मतलब कॉलम और बीम का कॉम्बिनेशन, जिसकी एक तरफ हिंज हो एक तरफ रोलर हो, तो इसकी प्रैक्टिकल एग्जांपल दे दें।
नीचे फाउंडेशन की बता रहे हैं आप?
जी सर।
फाउंडेशन की बता रहे हैं, ठीक है। फाउंडेशन में अच्छा, इसमें ये है कि योर, if I understand your question, I think you want to ask questions, this question, okay. Like this?
जी
Sir,
सर।
is it your question? Question आपका
जी
ये है?
जी सर।
Okay, then I will explain this question. I will answer this question, but it needs time, and I have another meeting now at 1 p.m. So, can you give me time for next lecture? I will explain this, and please remember this question. This is a very important question, and if you have some other questions similar to this one, you want to try to understand the concept of the supports in practical situation, isn't it?
यस सर।
Okay, so please remember this question and ask this question again in the next lecture, okay?
ओके इंशाल्लाह सर।
Okay, thank you very much.
थैंक यू सर।
Thank you, okay? Thank you to all. Okay. I will leave the lecture now because I have a meeting at 1 p.m. So next time, inshallah, you will continue and you come up with your questions, okay?